Okay, so good afternoon, everybody. So let's continue what we started last time. Okay. So just I want to remind you quickly on what we did last time, or what we did last two lectures. I told you very simple. Any logic circuit or logic, we have two types of logic circuits. One type we call it combinational. Okay. And most of what you did so far, not most, all what you did so far is under combinational. The other one here, we call it sequential circuits. Okay. As I told you, the main difference between them is, in case of combinational, the output of the circuit only depends on the input, only the input of the circuit. Okay, and that's what we have done. That's what we did in truth table, right? So in truth table we have input, and in this input we have this output. Okay, nothing else. But sequential is different. In case of sequential, here the output depends on two things, not only one thing, two things. It depends on, number one, for sure, the input, similar to this one, but on top of that, it depends also on the state, or as you will see, you can say the current output or the state. Okay, that means for the same input, I may get different output based on what is the current state, as you will see today. Okay, or in details. So that means the output here does not only depend on the input, but also depend on the state as well. Okay. Oh, you forgot something. I didn't see it. That's okay. Okay, so that's what I told you before. Also, I started to explain latches and flip-flops. Okay, and it's very simple. Latches or flip-flops, storage unit. Very simple, storage. Every latch or flip-flop store only one bit. Okay, so, and the reason I'm explaining them, because they are main components here in sequential circuits. So always in sequential circuits, always we're going to use latches or flip-flops. Is that okay? And that's what the states, by the way. So as you will see today, the values of the flip-flops or latches are actually, that's what we call states. Anyway, so we'll see. And then I told you, I explained different types of latches. I started to explain one flip-flop last time, which is D flip-flop, and I started to talk about JK flip-flop. Today I'm going to talk about T flip-flop. Okay, so we have three types of flip-flops, so we're going to talk about D, JK, and T. Okay, I think in latches I talked about D, right? D latch, and what else? SR, right? SR and D, right? But anyway, the main difference between a latch, both of them are storage unit, but the main difference is latches, we call it, for latches, they are level sensitive, or triggered, level triggered. What it means? It means once you change the input, the output will change immediately. Right? That's why it's level sensitive or level triggered. Once you change the level, once you change the voltage here 0 to 1 or 1 to 0, the output will change immediately. Is that okay? But flip-flop, once you change the input in flip-flop, the output, okay, is not going to change immediately, but it's going to change at the first edge. That's why we don't call it level sensitive or level triggered. We call it is edge triggered. So in order to see the, for example, if I put something here, if I put input to reset the flip-flop, it's not going to reset immediately. You have to wait until a certain time, okay? That's why in flip-flop here we have a clock. We have clock. In flip-flop, we don't have a clock. The purpose of the clock is just timing. And as I told you, for example, if a clock is just a square wave this way, as you know, we have some if the flip-flop is triggered at rising edges, so we have two types of them, two types, okay? Either it is triggered at rising or at falling, not both, one of them, okay? And as I told you last time, if you see something like that, operator this way, and then I see here clock, that means this one is triggered at positive here. At we call it rising or positive edge. It's the same thing. Rising, or we call it positive edge or rising edge. Okay, that means when you change the input, for example, I want to make a reset. I put the input that can make a reset. Okay, the reset is not going to happen immediately, but you have to wait until it only operates at these times. This is the main difference between latch and flip-flop. Is that okay? If we put a bubble here, that means this one is going to be triggered at falling edges, not rising. Okay, so here. And the reason we use clock, by the way, we are going to use a clock all the time. This is practically most of the digital circuits, we use clocks, okay? Because the reason for that, for synchronization. Sometimes I need to do, I don't want to work right now. No, I want several devices, okay, to work at a certain time, a certain point of time for synchronization, okay? Any question? You have a question here? Or? No, this is a good question, because actually we have two types of sequential circuits, okay, as I'm going to explain. We have, I think the definition is very clear. The output, it depends on the input and the state. It doesn't say you have to have a clock. It doesn't say that, okay? But we have two types of them. One of them with clock and the other one without clock, okay? Both of them are sequential. But the one that's with clock, okay, or the one that use flip-flop, it's synchronized sequential circuit. So, okay, as long as you said this, I was about to make this definition, so I can make it now. Yeah, so I put it here. Yeah, so here we have two types inside the sequential circuits. We have two types. One type we call it synchronous. Another one is called asynchronous. Okay, synchronous again, synchronous, synchronization, all of that achieved by clock. That means this one is using clock. There is a clock here. And because you are seeing a clock, there should be a flip-flop. This one is synchronous. That means there is no synchronization. Okay? This one has to use a latch. Because in any sequential circuit, we have to use either a latch or flip-flop. Okay? So that's why if you look at this one here, as you will see, any sequential circuit, it should have a storage unit, either flip-flop or latch. Okay, or maybe here this one a latch. Okay, also it has combinational circuit as a part of it, as you will see. So I combine them together, okay, to make a circuit. But here, if the circuit is synchronous, that means I'm going to use flip-flop and we have a clock. If it is asynchronous, you know, in English when you say a, it means not. If it is not synchronous, that means there is no clock here. Okay. That means once you put the input, once you change the output will change right away. But both of them are sequential. Why? Because both of them, the output does not only depend on the input. It depends on the input and also the state. A state here means the storage value here in the flip-flops, as you will see, or the latch. Is that okay? By the way, most of the time we're going to use this one. I think this one is, we're going to use it most of the time, okay? So, in this course, what we did so far is combinational in this chapter and next chapter. And if we have, I think, yeah, at least this chapter and next chapter, also in the coming labs, we're going to move to sequential, okay, sequential circuits. Yeah, I think, let me see if I'm missing something. Yeah, that's what I'm explaining here. Yeah. I just want to bring this one to your attention. Usually, the propagation delay is going to make a restriction on the clock you have. I can't have a clock that's very fast. For example, okay, so this is the main point. Look here. I have a clock here, okay? So I have here For example, this clock is gonna work at the rising edges. Okay, how much time I have to put here? If I can make this time very, very small, I will be happy. That means your computer is gonna be very fast. You got what I'm saying? It's gonna be very fast because you can do a lot of things fast. Because remember, in every clock here, we are gonna do an operation, addition, subtraction, something. Okay, so that means when we have a small time or higher frequency, because as you know, the frequency is actually 1 over the time. Okay, so that means it's better. This is something desirable, right? To have higher frequency. However, not everything we wish we can do, right? So usually there are restrictions. One of the restriction here is the delay, right? So the propagation delay plays an important role in determining the minimum interval between clocks. Let me make it very simple. I have to make sure once I start operation here, I have to make sure I have enough time before I give you the second operation here until you finish it. You got what I'm saying? So that's why delay is making a restriction on how fast or the clock here puts. I should have enough time here for the circuit to finish its operation before it starts with something else. You got what I'm saying? So that's why it can't be very smooth. There is a restriction anyway. Okay? There are other restrictions like transistors. Remember, any gate you have it is made of transistors. Usually transistor also needs some time to change between off and on. There is other restriction, which is the heating. You know, when you have a very high frequency, the devices start to heat. Okay, that's why you need cooling system. So there are several restrictions, but at least for now, I want to bring your attention to propagation delay, how it is linked to the frequency here. Okay. So look here, guys. So now I'm only focusing on flip-flop. I'm only focusing only on latch. However, as I told you, these flip-flops, we are gonna put it in a circuit, as you will see in the next section. Next section, I'm gonna talk about how we can create a sequential circuit by making something like that. So now I'm only focusing on a flip-flop. Okay. So I'm gonna put it in a circuit. So that's why I'm gonna put some kind of combinational circuit here to make something, to make operation. Okay, but that's what I'm gonna do in the next section. That is sequential circuit. So let me finish the flip-flops we have. Okay, so last time I explained D flip-flop. Yeah, and as you see here in D flip-flop, it was very simple. We have only one input. This input we call it D, and then we have one output, we call it Q. This is just a prime of this one, so I can say it's another output. Okay, anyway, so we have D and the Q, and the relation between them is Q. Look here, this is very important thing. Q at t plus 1 is equal to D at time t. What this means? Look here. That means if you have here 0 at time t, t plus 1 means when the edge comes. Okay, so usually we use something like t plus 1 and t. This is t before the edge comes, and this one after the edge comes. You got what I'm saying? So if you put here number 1, okay, before that is d of t. Once the edge comes, this one is gonna come here and to change the state. State here it changes from whatever to 1, right? Which is qt plus 1. I want you to understand this one. When I say qt plus 1 and the d of t, what it means? It means if you have a clock, we agree it has to work on a certain clock. In this case, it is falling, not rising. But anyway, if you have another one, but here it is falling. Oh, that's okay. So here, whatever before the clock, I call it a time t. Anything after the clock, so this is going to be the new state. For example, very important thing, okay, to understand. For example, if you have here 1, and then I put here 0, is that okay? So the current state is 1. The state at time t, the current state is 1. Okay, so I can say Q of t is 1, D of t is 1. When the clock comes, we call it Q of t plus 1. What is this? It's gonna be, this 0 is gonna come to here, so it should equal to 0. I'm sorry, this is 0, right? Should equal to this one, equal to 0. Is that okay? Don't be confused between t and t plus 1. T means before the edge. Once the edge comes, the new state, because we change the state. So here the state is 1. I put here at the input is 0. Okay, so what is the state? State is 1. Once the clock comes, the new state is going to move from from 1 to 0. Okay, the way you are gonna express this is, as I told you, I'm gonna say Q of t equal 1. This is the current state. D of t, this is the current value of t, equal to 0. Is that okay? Q of t plus 1, when the clock comes, the new state, okay, is gonna become 0, which is equal to this one. That is why we are saying here Q of t plus 1, when the clock comes, equal to d of t, the current value for t. And this equation, we call it a characteristic equation. So the characteristic equation is going to tell you the new state or the new storage value, okay, based on the input. Okay, so this is the characteristic equation for this flip-flop. The characteristic equation is Q of t plus 1 equal d at time t. You understand what I mean by t and t plus 1? Okay, because I'm going to use it all the time. Any questions? Okay, so that's what I explained for D flip-flop. I give you several examples here to understand how it works. And also I give you another one for positive edge. And this is how it looks like as a symbol, how it looks like, okay, for clock. And so this is for D flip-flop. I explained it last time. Last time also I started quickly at the end of the lecture. I started to explain the second one because I told you I'm going to explain three types of flip-flop. One is called D, and I already explained this one, JK and T flip-flop. Okay. Again, all of them are the same. All of them are a storage unit. All of them have clocks. Everything is the same. They are only different in the inputs. Some of them have one input. Some of them have two inputs. So JK has two inputs. D has one input. T has one input. Also, they are different in what value for the input is gonna change the output. How the input will change the output. Okay. So for D, I already explained the characteristic equation, which is Q of t plus 1 equal D at time t. Okay. This is a characteristic equation for this one. Now let's look at JK, how JK works. Okay. JK, as you see here, this is how it looks like. Okay. It has output Q. Always we have Q prime. That's always. Okay. We have a clock here. And from this clock, you can tell this is active high. So only action will be taken here. Active, or no, sorry, it's not, we don't say it active high. I'm sorry. We say it positive edges or triggered. It's triggered at positive edges. Okay. Or rising, triggered at rising edges. Okay. Anyway, now let's see. Now we have two inputs here, JK. Okay. So let's see what values for G. You know, if you have two inputs, that means you have 4. If you have 2 bits here, J and K, 2 bits, that means you have 4 inputs, 4 different cases, right? So let's see, very simple. Look how it works. I'm going to summarize it here. So we have J and K. Okay. If it is 0, 0, that means no change. Very easy. So if you put here 0, 0, okay. And now this one is 1. So when the clock comes, it's going to stay 1. If it is 0, it's going to stay 0. No change, okay? And that's what you see here. So here I'm telling you if it is 0, 0, okay? And then Q is 0 and 1, it's going to stay the same. You can see here, I use here N, I use N plus 1. It's the same like T and T plus 1. It's the same. So this is a current state. This is a next state. Is that okay? So if this is 0, it's going to stay 0. If it is 1, it's going to stay 1. No change. Is that okay? Let's see the next one. The next one here is, if you can put here 1 at K, 0 here. So this is the reset case. So if it is 1 at K and 0 here, this is reset. So that means we are going to put here 0, and for sure it should be 1 here. And this is, as you see here, but again, this should happen for sure at clock. Okay. If there is no clock, no change. I don't need to say that. Okay. If there is no, only changes happen here at the clock. anything between the clocks, no change, okay? Because it only works at the clocks, at the edges, okay? Anyway, let's look at the second case. If it is 0 and 1, 0 and 1, okay? As you see here, even if it is, if it q in here, if 0 is gonna become 0, 1 is gonna become 0, so it's gonna be 0 anyway, okay? The next case is when j is 1 and k is 0. This case is called a set, okay? So if you put here 1 and 0, this is the set case. Set means this is 1 and this is 0, okay? And that's what I did here. If you see here, okay? So no matter what value you have here, always we're gonna get 1. Set case. The last one here we have is actually 1 and 1. 1 and 1, this is toggle. Toggle. What toggle means? It means if the flip-flop is storing 1, so it becomes a 0. Storing 0, so you flip the stored value. Is that okay? And it's very, very clear here. You see here when it is 1 and 1. Look here. If q is 0, it's gonna become 1. If it is 1, it's gonna become 0. You toggle the stored value. Is that okay? So again, how it works? This table is explaining how it works. We have 2 inputs: 0, 0, no change; 0, 1, reset; 1, 0, set; 1, 1, toggle. Okay. For sure, this is different from the D flip-flop. In case of D flip-flop, when D is 0, Q is 0. D is 1, Q is 1. Okay, it's different. Okay. So how can we make it? Okay. The way we can make it, as you see here, or this is the structure inside here, inside this one. We can make it out of D flip-flop. So as you see here, yeah. So this one is D flip-flop, okay? So as you see here, what can we do? We can get Q prime here. So this one is Q prime. This one is J, okay? This one is Q. This one is K prime. Is that okay? And then here we have what we're gonna have here, Q prime J, and what we have here, K prime Q. And then we're gonna have here at Q here, at G here is actually Q prime J or K prime Q. Okay, so and this is, and as you know, Q of T plus 1 equal D of T. Is that right? Yes. That means I can write here what we call the characteristic equation. Again, the characteristic equation gives you the relation between the new Q and the input, the current input, as I explained before. Okay. So here now I can say Q of T plus 1 is equal Q prime J or K prime Q, and all of this at time T. That's what we call a characteristic equation here. See, so this is the new Q of T plus 1 at time T, okay, should equal, and this one at time T. So best, and again, look here. But how this is similar to the truth table you have here, okay? So for example, if you just apply what you have in the truth table, you get the same result here, okay? For example, here, if you, just to give you one example, if I use this one 0 and 0, okay, and just I'm gonna show you, and now Q is 0. If I take these 3 values, apply here in this one, for sure I'm gonna get here 0. Okay, so this is just an equation that can describe or the table you have here. Okay, for example, I'm gonna show you now. Okay, for example, J is 0, so here is 0. So regardless of you have here, this one is 0. Okay, K prime is 1, and now Q here in this case Q is 0. That means Q prime. I think something is wrong here, because this one should be, yeah. Let me see. I think something is wrong here. Okay. Anyway, so let's see here. For example, again, I'm gonna do it again. This equation should be applicable here for all these inputs. Okay, so let's take the first example here. The first example, when J is 0, K is 0, and the current Q is 0, okay, the equation has to give you 0 here. Okay, so if you put here 0, okay, and regardless of anything else, this one is 0. Now K prime here is 1, and Q, yeah, Q this one is Q is 0, so the result is 0, as you see here. Okay, let's take another one. Okay, let's take another one. For example, let's take this one here. Okay, so here again, J is 0, so this one is 0 regardless of anything because J is 0. K prime here is 1. Q is 1. That's why I'm gonna get here 1. Okay, so anyway, so what I'm explaining here in case of D flip-flop, as you see here, number one, let me summarize what I explained. Number one, this is how this flip-flop looks like. We have two inputs, J and K, as you see here. You need to know how it works for the different outputs here. That's what I explained. Also, I explained how can you create JK flip-flop using D flip-flop. So this is actually whatever inside here, okay? And this is a characteristic equation. So this equation should give you the relation between QT plus 1, Q of T plus 1, and J, the two inputs, J and K, and the current state, which is Q. So the new output here, which D is equal to Q, right? So that's why it's the same. So here, Q of T plus 1, this is the next state, okay, or next output. It means when the two inputs you have J and K and the current Q. Okay. Any questions? Okay. So let's have to also better to understand it more. Let's have sometimes these diagrams are very important. Okay. And before I forget, next week we're gonna have quiz number 5. Okay. In quiz number 5 is gonna have 3 questions. Okay. They are the same. It's the same. I'm gonna give you clock. I'm gonna give you 3 questions for each flip-flop, for D flip-flop, for JK flip-flop, and also for the T flip-flop, as I'm gonna explain right now. Okay. So for each one of them, I'm gonna give you the clock. I'm gonna give you the input. Ask you to give me the output. That's it. To draw it. Okay. For the 3. So exactly it's going to be similar to something like that, but for sure I'm going to make some changes, but it will be something like that. Okay. So let's see here how it works. So this is the initial value here. We are starting from here. This is a very initial value. And here, so as I told you, just to make it easy, you need to look only at these points here. You need to only look at this point, at rising edges. Anything in the middle, it's no change. Okay. So that's why it's going to change. The flip-flop is going to change its value only at this point here. Is that okay? So let's start with the first one. Okay. Here in the very beginning, it is 0 and 0. Okay. Yes. Wednesday. So here, J and K is 0, 0. And you know 0, 0 means no change. Okay. That's why in the initial, Q is 0. So no change. It's going to continue 0. That's it. Is that okay? Now let's look at the next one here. This clock here. Now, at this point here, the situation is different. This is 0 at this point, and now this one is 1. 0 and 1. Input change, 0 and 1. And you know 0 and 1, when J is 1, K is 0, is going to be a set. That's why this one is going to change to high here, based on the input, because it's set. Same thing when I come here, when I look at this one here, it is now 1 and 1. You know 1 and 1 means toggle. So now because this one is high, when the clock comes here, it's gonna turn it to low. Is that okay? Let's look at the next one here. I'm gonna look at this point. At this point here, it is 1 and 1. You know 1 and 1 means toggle. So what's gonna happen at this point? We're gonna toggle from 0 to 1. Okay. Let's look at the next one here. So here, this one actually at this point here, it becomes 0 and 0. Okay, so it's gonna go to 0 and 0. You know 0, 0 and no change, because this one is high, it's gonna continue high, no change. Okay, and then for the next one here, also it is 0 and 0, 0 and 0. Okay, 0 and 0, it's gonna be also no change, so it's gonna continue high. If you look at what happened here and this clock, in this clock, it is 1 and 1. 1 and 1 means toggle. Okay, so toggle, it was 1, it becomes 0. Okay, next one here, we have here 1 and 1. 1 and 1 means toggle, so it's gonna come high again. Any questions? I think it's very easy. It's just two things. Number one, you have to only look at the edge. In this case, it is rising edge. Okay, maybe in exams it's going to be falling edge. It doesn't matter. So if it is falling, so in this case I have to look at the other edge. I have to look at this one, and then this one, and so on. Okay, see what is the input, and then you already have a table, and then see how the output, new output will be. Okay, any questions? I have another example here for you. I can explain it quickly. So for example here, initially, Q is 1 initially, okay? So here in the very beginning, we have, it was here, the very beginning, it was 1 and 1, so that's why it's gonna toggle to 0, okay? And then let's see what happens here at this moment here. At this moment, so this one is 1, and this one is 0. 1 and 0 is gonna be set, that's why it's gonna go high. Let's look at this one here. So this one is actually 1. Also, this one is 1 here. Okay. So this one is gonna toggle to low. Okay. Here is still the same. 1 and 1 is gonna toggle to high. Here, this one here becomes 0 and 0. Okay. So if you are confused, if there is an edge here, try to see a little bit after the clock. So after the clock here, it becomes 0 and 0. 0 and 0, no change. So it's going to become high, stay high. Same thing here. It is 0 and 0, no change. It's going to stay high. Okay. Here, this one is 1, and this one is 1. 1, 1, toggle. So it's going to become 0. This is for Q. Q prime always the opposite of Q. Okay. You just flip Q. Any questions? Okay. So I just want to tell you here, similar to what I explained to before, we can add preset and clear as I explained to before, and they are going to act exactly the same way as I explained to before. Once you have clear, so the flip-flop is clear, is 0, regardless of the clock, immediately, similar to what I explained before. Also, I want to tell you, because if you search online, or in case if you read another textbook, or even in case of Zybox, you can sometimes we do it in different way, but the function table is the same. Okay, so for example, look here, it's exactly the same thing. So for example, if you come here, the way I did this one is using AND here and OR. Okay, so sometimes we can do it using NAND, and NAND. Okay, so which is the same. So both of them are gonna have, even when I calculated the characteristic equation, I got the same thing. And even if you remember early in this course, when I told you if you have AND OR, this one can be implemented using NAND. Anyway, so just this is just a different way. But both of them are exactly doing exactly the same thing. Even whatever you are going to get here is similar to what we had before. You got what I'm saying? So these two combinational circuits are equivalent, but just a different way. Any questions? Yeah, sure. This is clear and reset. Yeah. So yeah, similar. Yeah, maybe I need to write here, but I just said here it's just similar to what I explained in G flip-flop. Okay. So sometimes they come with clear and reset, similar to what we did before. Okay. I don't need to explain it again because it's similar. Everything is similar to what we did before. Okay? The last one we have here, we call it T flip-flop or toggle flip-flop. Okay, this one has, if you look here, this one has only one input. We call it T input. Okay, only one input, similar to D, one input. However, the function table here is different. In case of D, remember, in case of D flip-flop, okay, it works this way. If D equal to 0, Q is equal to 0. If D is equal to 1, Q is equal to 1. Remember when I told, yeah, Q is equal to D. This is, here it is different, okay? Here we have only two cases, as you see here. We have case, if T is equal to 0, no change. 1, toggle. So we don't have set or reset. All what we have, no change or toggle. So it's different from this one, okay? So in case when T equal to 0, that means no change. When T equal to 1, it means, or what's going to happen is actually toggle. So you have two cases, either no change or toggle. This is for T flip-flop. Any questions? Okay, before I give you details, let's see. Yeah, let's look at this example here. Okay, again, this one is going to work at, for example, rising edges. So it's going to work here at rising edges here. Okay, initially, at this moment here, T is 0. You know, 0 means no change. Initially, it is 0, so it's going to continue 0. Okay, no change. Let's look at this one here. At this moment here, T is 1. You know, 1 means toggle. Okay, so it's going to toggle to high. Okay, and then look at this one here. It is 1. 1 is toggle, so it's going to toggle to 0. Toggle means a flip. You flip it. Okay, so same thing here. It is 1. You toggle. Okay, same thing here. It is 0. 0 means no change, so it's going to continue the same. Okay, this one here, it is 0, no change, so it's going to continue the same. So in the quiz, I'm going to give you this one. I'm going to give you this one. I'm going to give you the initial value here, and then I'm going to ask you to draw this one. Just to test you, I want to make sure you understand how it works. And you need to know them very well, because we are going to use these flip-flops all the time. We have only 3. We have D flip-flop, we have T flip-flop, we have JK flip-flop. You need to know the 3, how they work very well, because we are going to use them all the time. Any questions? Similar to what I did before, I'm going to explain how we are going to make this T flip-flop out of the basic one, which is the D flip-flop, the basic one. Also, I'm going to explain how can we make the characteristic equation, okay? So actually, the way we can do it, yeah. So this is actually the structure. So so this is actually whatever inside here, the structure of it. So the basic one is actually the D flip-flop. This is the basic one. Anyway, so how can we make it? As you see here, all we need here XOR, and then we put here T, and then we put here Q. That's it. And then this will be input to D flip-flop. If you do this way, you created T flip-flop. How it works? By the way, it's very simple. I'm going to tell you how. Remember, when I explained XOR, how I explained it? When I explained XOR, I told you, if you have 0 and X, you are going to get X. And if you have 1 and X, you are going to have X prime. This is how XOR works. Is that okay? It's exactly the same thing here. If you have here 0, and then you have here Q, okay? So this one is Q, so it's gonna Q again is gonna come here. So no change, no change. It's the same value. Whatever you get from here, if you get 0, 0 is gonna come here and then get out here. No change. You get what I'm saying? So if you put here 0 and here a Q, you are gonna get Q here. So whatever the value you have here, you will get it again, no change. Okay. But if I put 1, if I put here 1 and we have here Q, oops. So we're going to have here Q prime. This is how XOR works, Q prime. And then because this is a D flip-flop, this Q prime is going to go outside here. That's why it is toggle. It's toggle. So if you have here 1, this one is going to become here 0, and then next in the next state, 0 is going to go outside here. Very easy, right? Any questions? Okay. So in this case, what is the characteristic equation here? Again, characteristic equation means it gives you a relation between the new state or the new Q value and the input, okay? And the input and the last Q values, okay? So in this case, I can say here, Q of t plus 1, the new Q equal D of t, equals the value of t at time t, okay? And actually, D of t, as you see here, is actually t, for sure, at time t, XOR with Q at time t. So the characteristic equation here, we can say the new Q value equal T XOR Q. Okay, so this at time T, and this is the new value. Okay, so the new value, new state is equal the current value when the clock comes. Okay, so when the clock comes, the new Q equals the current before the clock comes, T XOR with the current Q at time T before the clock. Anything at time T before the clock, will be after the clock. That's what we call characteristic equation. It gives you a relation between the new output I'm gonna get and the input and the current, the present or current output Q. Okay. Yeah, before I take the question, even if you apply here, if you look at the truth table here, if t is 0 and Q is 0, I'm gonna get 0 because it's no change. If Q is 0, T is 0, Q is 1, I'm gonna get 1, no change. Okay. In case of 1, it's gonna be toggle. So you see here, these ones are toggled here. Okay. It's the same thing. If you apply here in this equation, you will get the same result is here. Okay. Because this equation actually it gives you the relation between the current T and the current Q and the new Q. Yeah, what's the question here? Sorry, raise your voice. Okay. Okay. Any questions? Yeah, I think that's it. So here I just summarize what I explained because this will be the quiz. You need to know them very well. So number one, I explained TD flip-flop. You should understand how it looks like. You have input D, you have clock, okay, and then you have output here. And this is the function table or characteristic. We call it function table or characteristic table. Okay, this is how it works if very simple. And the characteristic equation Q of t plus 1 equal to D at time t. Okay. The second one here, GK flip-flop, and this is a truth table or characteristic table as I explained, and this is how it looks like. Okay. The last one here, T flip-flop. So in the coming quiz, there will be 3 questions: one for T flip-flop, one for D flip-flop, one for GK flip-flop. Is that okay? That's it, and that's what I explained here about synchronous and asynchronous sequential circuits. Any questions? Okay. Now we're gonna start talking about sequential circuits in more details. Okay. As I told you, as you see here, any sequential circuit, it should have, if you look at what we did here, any sequential circuit, usually it has a combinational circuit in addition to flip-flops or latches, but we're gonna focus on flip-flops. So flip-flops are actually building component of the sequential circuit, okay, as you will see now. So in this section, I'm gonna explain, and this section needs to pay some attention to it. I hate to use the word difficult, but a little bit confusing. Once you understand it, you will feel it's very trivial. If you don't understand it, you will feel it's like too complicated. Okay, nothing is complicated once you understand it. Okay, so but I just comparing to what we explained before, this one needs some attention from you. Okay, so what I'm gonna do in this section, I'm gonna analyze collective sequential circuit. So what do you mean by analyze? Analyze mean so let's first talk about how we did in combinational circuits. Okay, how we analyze. Analyze means I wanna study the behavior. I wanna know how the output will behave, or how the output changes when the input changes. Okay. In case of combinational, it was very easy or straightforward, because the output only depends on the input. So what I did, for example, if just an example, if you give you a circuit like this one, I tell you this is X, Y, and then I do here something like that. I see this is Z. This is a combinational circuit, right? So the way we analyzed it, or in order to get the relation between the output and the input, the way we did it is, you can make like a truth table. That's what we did, truth table. All what we did, we put all different cases here, X, Y, Z, and then you put here all possible cases like 0, 0, 0, 0, 1, 1, 1, 1, 1, and then 2 zeros, 2 ones, 2 zeros, 2 ones, then 0, 1, 0, 1, 0, 1, and then we got F here. Okay, we put F here, and this is F. And for every input here, I calculated for this input, what is the output? The output is 0. For this one, what is the output? Output is 1. Output is 0. Output is 1, whatever. Okay, so but using this table here, I can know the relation between F and the input, or how the output is going to change when you change the input. Is that okay? I want to do the same thing, but for sequential circuits. But it's not going to be straightforward like this one. Why? Because here the output only depends on the input. For the same input, I'm going to get the same output. But in this case, the output depends on the input and the current state. That means for the same input, maybe I'm going to get 2 different outputs based on the state. Again, a state means the values of the flip-flops based on the current values of the flip-flops, as you will see right now. So again, I'm going to explain how we are going to do it, but you should understand what I'm doing. What I'm going to do right now is similar to what we did before when you have a circuit like that and then you get a table like this one. I want to do the same thing, but for sequential. But it's going to be different, because in case of sequential, I'm not going to only look at the input. Also, I need to know what is the current state and then calculate what would be the new state and the new output. You will see right now, okay? Anyway, okay. There are some definitions here, but I'm going to come to this definition after at least explain. I have 4 examples here to understand it. Let me start with first example here. Okay. So now we have what we call a sequential circuit. So what is the sequential? This, what you see here is a sequential circuit. Any sequential circuit should have at least flip-flops, as you see here. This one has 2 flip-flops. Is that okay? Also, it has combinational circuit outside here. Okay, so everything here we call it sequential. The basic form, the very basic form of sequential circuit, just 1 flip-flop, right? But you can use you don't need to use combinational all the time, okay, to create a sequential. But you must use flip-flops for sure. Here we are going to focus on synchronized. That's why you are going to use flip-flops instead of latches. Okay. So as you see here, what we have, this circuit is sequential circuit. Any sequential circuit should have flip-flops. We already have flip-flops. Sometimes, or most of the time, on top of the flip-flops, we have also some sequential circuit, as you will see here. Okay, this number 1. Number 2, all the flip-flops are connected together using the same clock. Any sequential circuit, we do that. Here in this example, we have 2 flip-flops. Maybe in another circuit, we have only 1 flip-flop. Maybe in another circuit, we have 100 flip-flops. All of them are connected together using clock. Okay. Number 3, this circuit has what we call input. This is input. So input coming here. Okay. So you need to input some value here. In this case, we have only 1 input. In other circuit, you may have 2, may have 3. Okay. But in this case, we have only 1 input here. Also, this one here, we have 2 states. 2-bit, it's 1 state, but 2-bit. So a state here, what state means? The values of the flip-flops here. Okay. So if the flip-flops are storing 0, 0, we call it, this is the state. So state means the current value of the flip-flops. So as you will see, the word state means the values of the flip-flop. So in this case, because we have 2 flip-flops, every state is going to have 2 bits. Like, for example, 0, 0. So that means you're storing 0, 0 here. This is the state. Is that okay? Or 1, 0, or 1, 1, 0, or 1, 1. Okay? Because we have 2 flip-flops. How many states you may have in case of 2 flip-flops? 4. So here, this circuit can have up to 4 states. 0, 0, which means this flip-flop is storing 0, 0. Okay? Or 1, 0, or 0, 1, or 1, 1. Okay? So I have 4 states. Is that okay? And then, based on the input here and based on the clock, we're going to move from one state to another. So, for example, I'm going to explain, after I finish, I'm going to explain something like that. Okay? A state diagram. So in this state diagram, this one actually is describing the behavior, how the circuit works. So 0, 0 here, again, because we have 2 flip-flops, that means we have 4 states. We have state 0, 0, we have state 1, 0, 1, 1, or 0, 1. These are all possible cases, okay? Again, state, the values stored by the flip-flops. Is that okay? And then, based on the input here, what happens is that every time there is a clock, every time clock comes, if I'm here 0, 0, based on the value of the input, either we're going to stay here 0, 0, or we're going to move to this state based on the value you have. Okay, so these transitions happens at the clock. Okay, so I'm here, maybe I'm going to make a transition here at the clock based on the new value or I'm going to make a transition to here. Okay, for if I look at this one, how many, if I'm here in this state, I have 2 cases. When the clock comes, either I'm gonna stay here, the values of the flip-flops will be the same, or this one is gonna come here. Okay, these transitions happen at the clocks, at the edges. Okay, and actually it depends on the value of the input x. For example, here I'm saying when x is 0, if x is 0 and the current state 0, 0, when the clock comes, I'm gonna stay here. If x is 1, when the clock comes, I'm gonna move to here. Don't worry, maybe it's somehow a little bit complicated. It's not similar to what we did before, but what you should understand now is the system has what we call a state. Every circle here is one state, and because we have 2 flip-flops, so we have 4 states. Because what these numbers here, these are the values stored in the flip-flops. Okay, so that's what you should understand. Also, what you should understand, what happens every time there is a clock transition happen. These transitions happen at the clock at the edges of the clock. Okay, maybe at some point I'm here. When the clock comes, I'm gonna stay here. Another clock comes, I'm gonna come to here. Based on what? Who's gonna decide if this one is gonna stay here or come to here? X, the value of x. Okay. Also, anyway, slowly, I have 4 examples. If you understand one, all of them are exactly the same thing. One of the things you see here, so again, any sequential circuit should have flip-flops. This number 1. Okay. And because it has flip-flops, you have what we call states. Okay. States is in every state. Every state should tell you what is the stored value here in the flip-flops. Also, sometimes we have input, like input here. This input can be 0 or 1. Okay. And also, sometimes we have output. Here, as you see here, this output is taken from a combinational circuit. So here I have a combinational circuit right here, and this combinational circuit is taking values. For example, if you look here, this is taken from x. So this is coming from x. Some of these are coming from the states or from the output here, A, the output of this one. This one also is coming from B. So actually, let me write it here. So this is x, this is A and B. A and B are actually the stored value here in the 2 flip-flops. Okay, and then I'm gonna make a combinational circuit, and this is what we call output here. Okay, there is a tricky point here. Listen to me. Usually, when I do a combinational circuit like this one, to get output, usually we call it output. Is that okay? However, sometimes the real output of the circuit is coming from A and B, the real output. But just to differentiate between them, between A and B, and anything coming from I'm going to call this one output. But as you will see right now, sometimes we don't have output like this one. But in this case, the circuit is taking the output, is a real output from A and B. Is that okay? So this is what I want to say. So here, this is one example for a sequential circuit. It has flip-flops. It has, as I told you, should understand what I mean by states. It has input, okay? And it has here clock. All of them should be clocked together. So that means these two flip-flops are going to change at the same time. At the same time, because they are clocked together. The same clock here, okay? Also, we use here at the input here, I'm using combinational circuit. At the input here, I'm using a combinational circuit. Here, I'm using a combinational circuit to get what we call is output here, okay? Anyway, so now the question is that if I give you, that's what I want to do in this section. What I want to do in this section is, if I give you a circuit like this one, can you make, can we analyze it? What do you mean by analyze? I want to do something like the truth table we did before. I want to know by changing the input, how the output will change. I want to get the relation between the output and the input. That's what I mean by analyzing. Similar to the truth table, right? But here, it's here number one is, I'm not going to call it a truth table. I'm going to call it a state table. So if you look here, that's what I'm going to explain to you now. So in order to analyze this one, instead of making what we said before truth table here, I'm going to call it a state table. Okay. So what is the truth table? State table. So as you see here, the state table here, I put the flip-flops A and B. So as you see here, we have two flip-flops. The output of the first one, I call it A instead of Q. Okay, so just because we have two, I can say Q and Q, otherwise I will be confused. So I'm going to call this one instead of Q, I'm going to call it A and B, the output here. Okay. Also, because again, you understand what I'm saying, guys? So here again, because you have here Q and Q, when I say Q, which one do you mean? Very simple. I'm going to call the output here our A and A. Okay. Instead of Q and Q, I'm going to call it A and B. Okay. And now, because we have G here and we have G, how we can differentiate between them? Very simple. I'm going to call this one G subscript A. This one, I'm going to call it G subscript B. Is that okay? Just to differentiate between them. So when I say G of D subscript A, that means the input here. D subscript B, that means the input here. When I say A, means the output here. When I say B, means the output here. Is that okay? Just to differentiate between them. So what we want to do, in order to understand how this circuit works or the relation between the output and the input, okay, I need to create a state table. And the state table is similar to the truth table, but it's a little bit more complicated than the truth table because the output does not only depend on the input, also it depends on the current state. Okay, that's what you will see now. So how, number one, so what I'm going to teach right now, or what I'm teaching in this section, what I'm teaching in this in this section, given a circuit, how can you create the state table? And then after we create the state table to give you the relation between the output and the input, I'm going to also explain to you, if you have a state table, how can you present it in the form of a figure? We call it a state diagram. Okay, state diagram and state table, both of them are giving exactly the same information. There is no difference between them. The only difference is this is just in a diagram or in a graph, but this is a table. So these two are exactly giving you exactly same information, but in two different ways. Is that okay? So let me first focus on this one, because you have to get this one first, and then from this one you need to draw this one. So let's start with this one first. Okay. So, okay. You understand what I'm doing right now, guys? What I'm doing here, similar to what you did before when you did the truth table. I have input, you need to calculate the output. Exactly same thing. But this is for sequential. It's a little bit more complicated. Again, so here, how the state table looks like and how I'm going to make it. Look here. First of all, you need to put this part here in the left here. You have two flip-flops. So I'm going to call it A and B. Okay. This is the present state. Okay. And have another input X. It is like you have three inputs, because the output is going to depend on the three values here. Okay. The output is going to depend on the three values, the current state and also the input here. Okay. So this is similar in the truth table when you had X, Y, Z and put all possible cases. That's exactly what I'm going to do right now. So here it's like I have three. It's like you have three inputs, but actually I'm not going to call it inputs, because these two are called the current state or the present state. Okay. And then here you have to put all possible cases as we did before. 0, 0, 0, 4 zeros, 4 ones, 2 zeros, 2 ones, 2 zeros, and so. Okay. Is that okay? So again, in the slides here, I have 4 examples. If you understand one, all of them are the same idea. So number one, here you have to start with this part here. In this part, you have to put the flip-flops here, A and B, E, this one and this one. Okay. And then you have to put the input here. And then you have to put all possible cases as we did before. Okay. All possible. Is that okay? Any questions? And then after that, for each one of these, you have to calculate the current Y, the current value for Y, and also you need to calculate what is the when the clock comes. Given these inputs, when the clock comes, what would be the next state? What is the next A and B? Okay, so that means, so now this part you have to write it, and then you have to calculate this part. I'm going to tell you how you have to calculate it. But what it means if the current state is 0, 0 and X is 0, okay, that means the current Y is 0. So Y here is the current. And the new state, when the clock comes, okay, I'm going to move from 0, 0 to 0, 0. So A and B are 0, 0. When the clock comes, X is 0, I'm going to move to 0, 0. This is the meaning of this record. I'm going to explain how we can calculate, but I'm explaining the meaning of it. Same thing here. If you look at the next one here, let's look at this one, for example, here. This one means if the current state is 0, 0, A and B are 0, 0, X is 1. Is that okay? So the current Y, the current value for Y is 0 before the clock. When the clock comes, we're going to move from 0, 0 to 0, 1. It's the new state. Okay. So, okay, but let's first see how we are going to fill up this table. So assume nothing is here. I told you this part, you just put all possible cases here. Let's see how we are going to fill up this part. Okay. So what you can do here, look here. Let's very simple. All what you have to do here, what is first of all, what is the value of Y? So we need to know the value of Y here. Okay. So Y here is actually equal to, here this one is X. So this one is actually X prime. Okay. And then here we have B, if you see here B. And then we have here A. So it's going to be A or B. Okay, so first of all, I need to get the equation for Y in terms of X, A, and B. Is that okay? So based on, as you see here in the figure, and that's what we call the output equation. So need to get this output equation here. So the output equation I have is Y, okay, at time t, this Y at time t is actually equal B at time t, A at time t, before the clock comes, and they have X prime at time t. It has to be this way. And then I'm going to tell you, because everything here in the time t, I don't need to keep saying time t. That's why always I'm going to say, for this output, Y equal B or A, X prime. So I'm going to remove t, because always, so here, we're going to say Y equal B or A, X prime. Because always the output equation at time t, before the clock. Currently, this is always it's like that. So no need to say t. Always it's going to be like that. Okay. So this is the value of Y. So Y equal B or A, X prime. Is that okay? So if I come here to this table, I can calculate all of that. Very simple. Very simple. So y should equal a or b and then x prime. That's it. But which one you are going to use? Are you going to use this a and b or this one a and b? Which one? I'm going to use this one at time t, because this one at time t plus 1 and y at time t. So y here, this is the current y before the clock. Okay. So all what you have, just you have this equation a or b x prime, and then you can calculate all of this one. So if you come here, you have or 0 or 0, okay, is 0 or 0 is 0, and anything is 0. So that's why I got 0 here. Okay. If I, for example, let's look at this one here. I'm gonna come here. Okay. So here you have 0 or 1. It's 1, right? And then x prime is 1. 1 and 1 is 1. You can calculate everything here. Yes. I did. No, the way you have to start is you have to put the states here and you have to put the inputs here. In this example, I have 2 states and 1 input. I have to put them here this way. And maybe in another example, you have 1 state and 1 input, or 1 state and 2 inputs. Whatever you have, just put them here and then put all possible cases as we did before in the truth tables. This number 1. Number 2, you have to get the equation for the output equation, this one. Okay. And this one, maybe the part that can confuse you is I have 2 values for a at time t and t plus 1. You got what I'm saying? This is after the clock comes. Okay. So always the output is going to be calculated the current output, not the future one, not when the clock comes. So that's why when I calculate the output, I'm going to use these ones, a and b. I'm not going to use the future ones. So now y is actually equal a or b x prime. So using this equation, I can just fill up this column here. Is that okay? Now, so what is left to finish this table? I need to know what is the next state here. I need to fill up this part. Is that okay? To fill up this part here, okay, you have to get to fill up this part here. I need to calculate the value of g here. I need to calculate the value of g here, because whatever you have here, this will be the future value for a when the clock comes, because this is d flip-flop. So I need to calculate the input here, okay? And this input actually will be the output, the same output when the clock comes. You got what I'm saying? So actually, a here should equal, this is just a special case in this one. So here actually a at time t plus 1. So the time t plus 1 equal d of a at time t, because this is d flip-flop. If it is t flip-flop, if it is j flip, it would be a different case, and that's what I'm going to address later. But now here, because this is d flip-flop, I need to know what is the current value for d, and this will be the future value when the clock comes, because this is how d flip-flop works. Okay. And actually this equation, we call it a state equation. So look here, guys. So we have another equation here. I'm going to explain it. We calculate what we call a state equation. So a state equation, all what I'm going to do here, what is the new value for a? The new value for a is actually equal d at time t. Is that okay? So whatever you have here at time t, it will be here at time t plus 1 when the clock comes. Make sense? So now the question is how I can get this value? Very trivial. You have here a, you have here x, and then you have here x, and then this one is coming from b. So you have b. So this one actually ax, this one is bx. So this one actually is ax or bx. All of them at time t, because I want to calculate d at time t before the clock comes. Okay, and that's exactly what I did here. This is what we call a state equation. So state equation is going to give you the new state, the new value for a, the new state when the clock comes, using the current value for a and b and x. So the new state, the new value here, it depends on the current value for A and B and X and the current X. I just calculated it from here. I see what is the value. Same thing here. This one may be simpler than this one. So let's look at this one here. If you look at this one here, what is D of P at time T? So what is this value here? Okay, let's see. So we have here B, we have here, this one is coming from A prime, and this one is coming from X. So this one is very easy, X, A prime. So it's gonna be, as you see here, so the new value for B, is actually the current value for A prime and X prime, which is actually dB at time T. That's what we call state equations. And again, because this part, look here, always this part is at time T. So always this part at time T. That's why usually, just to make everything is simple, and always this part at time T plus 1. So I'm gonna remove T from here, just to make it simple, because always this part in T, okay? That's why you are gonna write the equation this way. Two are state equation. So the new value for A is actually equal AX or BX. And because there is no T here, I mean the current value. Okay, guys? Again, once you have this one, can you fill up this one? For sure I can. Can you fill? Can you get this one here? Yeah, because you already have what I calculated here for the new value for A, which is A. So I have already equation for this one, A of T plus 1, which is equal to AX or BX. That's it. So all what you have to do, you have A here and X here. You just plug in this equation, you get the value of A. You can fill up this column. So again, I got a relation between this one is A T plus 1 because this is a new state. This is B of T plus 1, this one here. Okay. So I have a formula for the relation between this one and this 3. Just, yeah, as you see here, AX, A and X, or B and X. Just use this formula, I fill this one up. Same thing for B. So if I come to B here, we still have 3 minutes. Okay. For B, as you see here, for B, okay, B equal A prime and X. Yeah, so the relation for this one, B at time T plus 1 is equal to A prime, okay, and X. Is that right? Yeah, A prime and X. So all what you have to do here to calculate this one, B prime and X. Okay, you have B here and you have X here. That's it. So for example, here, X is 0, so this one will automatically be 0, regardless of what is B prime. This one is 0, so become 0, because regardless, 0, regardless, okay, because this is end. And now, if here X is 1, okay, X is 1, B prime is 1, so the output here should be 1. Okay, X is 1, something is wrong here. Okay, so here, for example, here, X here is 1, B prime is 0. Yeah, that's why you are going to get 0 here. Is that okay? Anyway, so once you have the relation here, you can just fill up these tables. Okay. So let me summarize what I said. What I said here, guys, is that the way given this table, given the circuit, I'm going to give you the circuit. Given the circuit, I want you to make the state table. This state table is similar to the truth table you had before, but this time it's a little bit more complicated because the output does not only depend on the input as we did before. Also, the output depends on the input and also the states, which is A and B. So that's why all what I did here, guys, I have 2 flip-flops. So I'm going to put the current state, A and B, which are the values of the flip-flops. I have one input, X. I'm going to put it. And then you are going to put all possible cases here. Is that okay? This is number 1. Number two, I'm going to get one equation. Using this equation, I can calculate y. I'm going to get two equations here. I'm going to calculate this one. Very simple. So how can you get the equation of y? And this one, we call it the output equation. Okay. The output equation. Yeah. So you can see here y is equal a. Okay. And this one is coming from b. Okay. This one, yeah, it's here, it's coming from b, and this one is coming from a, and the x prime. So if you can see here, y is actually x prime, b or a, this way. Maybe the part, I'm still saying it again, the part that may confuse you, which one at time t and which one at the time t plus 1. Y is the current y before the clock comes, not the future one. Is that okay? And then also you need to calculate. So using this equation here, you can fill up this one using the information you have here. Okay. I'm gonna do the same thing for these two. I need to get two equation. Okay. And the input of these two equations should come from here to calculate the values here. Okay. So these two equations, here, this is just a special case, because in case of this will be different, as I'm going to explain in the future, the other flip-flops. But for this flip-flop, I need to calculate the input here, because the current input here will be the new state when the clock comes, because this is how the flip-flop behaves. Okay, so that's what I did. So when I calculated the current input here given from this combinational circuit, I find it's this way. And then I removed the t, because this one is always at time t. So the new value for A should equal the current value for D, which is actually AX or BT. So using this equation, you can fill up this one here. And then it's the same thing here. Is that okay? Anyway, so next time I'm going to explain how can you, it's very easy. How can you, once the difficult part is how can you get table? Once you have this table, I'm going to show you how can you draw this one, because both of them are giving the same information as I told you. So if you have table, you can make a diagram. If you have a diagram, you can make a table and so on. Okay. So as I told you, Wednesday you are going to have a quiz number 5. It will be about, as I told you, the 3 flip-flops I told you. Okay. Also, the coming lab will be I'm going to give you a circuit, and then I ask you to do analysis like this one. I get you. Okay. So I know this topic may be a little bit difficult. That's why I have four examples here. Okay, so all of them are the same. Once you understand one of them, all of them are almost the same idea. Okay. Thanks.